Hello, everybody. I don't think this concurrent viewer count stays correct. I don't think it updates as quickly as I want it to. Maybe I should restart my computer sometime. It's been going for 4 or 5 days now. That might fix a couple of the little things. Alright. Let's get into three-wire single-phase systems. There will be some concepts that you'll have to understand combination circuits to get in here. But they're like we'll circle back. You got a couple more weeks. Do your homework, and we will circle back and hit this concept again before your next class or during your next class. Three-wire single-phase systems are used because this type of system provides a 240-volt system. A three-wire single-phase system is what your house has. It lets you have 120 volts and 240 volts at your house. All right. In a three-wire single-phase system, what is the maximum unbalanced load the neutral conductor must be able to carry? It is the full load of either leg. So in a three-wire single-phase system, you have let's just clear all of this. I have cleaned up my desk. Hang on. Just do it in my lap. All right. You have your red wire. You have your black wire. And since this is, I'll do gray, because gray is also, it's not really visible, is it? Oh well. We're going to work with it. And then, in between, you have your loads. Let's actually erase a little bit of this neutral. That's good. So this line is 120 volts, and this line is essentially negative 120 volts. Which, that's just direction. That's all that the positive and negative indicate in electrical. And this will be 0 volts. Remember, voltage is a difference. So if you were to measure from here to here, the difference is 120 volts. Measuring from here to here, the difference is 120 volts. So any loads that go from there to there is going to have 120 volts. From there to there is going to get 120 volts. And all the loads crossing from, we'll call this L1 and L2. Any loads crossing from L1 to the neutral is 120. L2 to the neutral is 120. You can also have loads that cross from L1 to L2, and that will be 240 volts, because the difference is 120 to negative 120 is 240 volts. And this is the concept around how your electrical system works. How you have 120 volts and 240 volts. The neutral, so let's say this was 5 amps and 7 amps. That's what each load is pulling. Well, the neutral is only carrying the difference because they are opposites. You could call this negative 7 amps because it's flowing against it. So essentially, if I wanted to put some arrows on this, this load is flowing like this, and this load is flowing like this. So one's pushing and the other's pulling. So if you're going over here, it would be like if you had some sort of sled and the L1 is behind the sled pushing on these, and L2 is in front of the sled pulling. So each load is its own sled. So L1 is going to be pushing with this force. L2 is going to be pulling with this force. Whatever right here, they're canceling each other out to be negative 2 amps. They have the unbalanced load, the difference between the two loads. Over here, L1 is pushing and L2 is actually helping pull on the same load, not different loads. So in this instance, it's actually getting more power. And that is how your three-phase system works. And it's alternating current, so they're 60 times a second they're swapping between pulling and pushing. But they are completely out of phase with each other. 180 degrees out of phase with each other, which means they're opposites. How much current flows on the neutral in a balanced 3-wire system? None. So in a completely balanced 3-wire system, that is where this is 5 amps and this is 5 amps. So that would turn this, whenever you check them, to 0 amps. That's it. It's simple. Dead simple. The trick is whenever you lose your neutral, then it turns into a combination circuit, not 2 parallel circuits. Because right now, this is just 2 separate parallel circuits that share this one line. You add a bunch of loads, and they're all just parallel loads. They're all just the same parallel load. There's no changes happening. Or they may not be the same, but they're all parallel. They're all getting the same voltages. Doesn't really matter what the amperage is. You would just add the amperages up to find the total load. Because it's just parallel. You don't need to know anything about combination. But as soon as this 0 volts goes away, this exit to the circuit, so you lose this connection, well, now it's a 240 volt combination circuit. So you can make the connection right here. Let's go purple. That's a selection tool. So this would be the circuit if you lose your neutral. It's a 240 volt series combination circuit. So all 4 of these loads are still in parallel, but now they're in series with the 4 loads that are down here. If it's all balanced, nothing changed. If it was a perfectly balanced load. Perfectly balanced loads don't exist, so that's going to be an issue. It's going to be looking for a way to balance itself out. And it makes things that shouldn't be hot, like shouldn't be electrified, become electrified because it's trying to create a neutral. connection, and you'll shock the fire out of yourself because you'll be like, you'll touch like the ceiling grid and it'll be hot, and you'll be like, what the hell just happened? In a 3-wire single-phase system, line-to-line voltage is 240 and line-to-neutral voltage is 120. I was just talking about that. Yeah. So what happens in this particular scenario? All of let's use a red box. All of these are going to have the same voltage, and all of these are going to have the same voltage. They will add up to 240, but this side might be this side might be 180 volts, and so that's not true anymore. This side is 180, and that side is just 80 volts. So everything on this side is going to burn up because nothing is designed to have 180 volts put across it. Nothing that's supposed to run on 120 is designed to have 180 volts. And everything on this side isn't going to work good either because it's like, this is your lights are going to dim. That's one of the first signs that you've lost your neutral before things burn up, because some things can take 180 volts for a little while before they burn up. Your lights actually dim. It'll be when you have large single phase loads come on, your lights are going to dim. So when you turn on your microwave, all the lights in the house dim, or half the lights in the house dim, or the TV shuts off, or something. Like, weird things start happening. I've been to a couple houses where this was happening, and I was able to find that they had lost their neutral somewhere. I had a house, my old house. We hooked up a travel trailer. It was a 30 amp single phase travel trailer. And we hooked it up, plugged it in, and we were getting it leveled out and stuff. We were running the AC, and that was a pretty big load, single phase. And I grabbed one of the leveling like levers, and it shocked the fire out of me. And I took a meter to it, and it had like 40 volts running across it. Like, that was touching the meter to it and plugging the other meter into the ground just to get some sort of voltage reading. So I was like, well, I don't know what the hell. And I mentioned it, this was whenever I was an apprentice. I mentioned it to my journeyman the next day at work, and he came to my house after work, and he walked right over to my transformer and pointed, like, yep, there it is. I knew that was it. So it's kind of obvious because really weird stuff starts happening. All right. So that is the end of this quiz. So let's start the last quiz. Last quiz. This is resistance and combination circuits. It's basically just going to be a bunch of circuits asking you what the total resistance is. It's not very many of them because I expect it's going to take y'all a few minutes to work these out. And I will work through these at like 5, my normal time. All right. I will see you guys in about an hour.